Welcome back to a course in Calculus RS Integration. In this lecture, we are going to see a theorem which is just an extension to the previous theorem that we have seen. In the previous theorem, we had seen the integrability of a function with respect to some unit step function, right? So let me state this theorem and see the significance and the relevance with the previous theorem. This theorem states that we have a sequence of non-negative terms, right? And this sequence of non-negative terms is given and summation cn, which means the series that form with respect to the sequence is a convergent one, and Sn is a sequence of distinct points, in open interval ab, and alpha of x is defined to be summation n runs from 1 to n cn multiplied with I of x minus Sn. Let f be a continuous function on closed interval ab. Then we'll have to prove integral a to b f d alpha. Integral f d alpha is summation n runs from 1 to infinity cn f of Sn. Okay. Here, let us pay some attention to understand what is given in the statement. If you see, initially I have told you that we have a sequence with which sequence of non-negative terms, and based on which we have formed a series, and that series is convergent one, right? And we take some sequence in the open interval a comma b, right? So what about this sequence Cn? This may be taken anywhere in the set of non-negative real numbers. But this Sn is a sequence which is taken in the open interval AB, and alpha of x is defined to be summation n runs from 1 to infinity Cn I of x minus Sn, right? And f is given to be some continuous function in the interval AB, and we'll have to prove integral a to b f d alpha is summation n runs from 1 to infinity cn f of Sn. So this is what we'll have to prove. Okay, let us get into the proof. Now, if you observe, for all n runs from 1 to 3 infinity, absolute of cn multiplied with I of uh, what x minus Sn, right? Okay, what is it going to be? This has to be compared with cn. We know cn is a sequence of non-negative terms. So it may be either 0 or some positive quantity. And similarly, this I may be either 0 or 1. So if it is 1, Cn is going to be equal to 1. If it is 0, 0 is to be compared with Cn. So this is the inequality that we are going to have. And of course, so this is the inequality that we are going to have. Okay, let us have like this. Or even if we have like this, there is no bother, because it is always a non-negative quantity, right? Therefore, by comparison test, summation n runs from 1 to infinity cn I of x minus Sn converges, since summation n runs from 1 to infinity cn converges. Because of the convergence of summation cn, this one converges, right? Whether you have absolute sign or not, there is no bother. Okay, so next we are given that alpha of x is summation n runs from 1 to infinity Cn I of x minus Sn. We'll have to prove this alpha is monotonic increasing function so that the integration with respect to this alpha can be spoken. For which, let us consider 2 points. Let x comma y be any 2 points on the interval a comma b with the condition x smaller than y. So if this is going to be so, then using the previous theorem, in the previous theorem also we have seen three cases whether s is smaller than x and y or s is between x and y, and this is after this x and y. We have considered three cases and we have proved your I of x minus s is smaller than or equals I of x minus, sorry, y minus s. This is what we have proved. There we have proved for a single point. Here we'll have to do it for sequence of points. So this is going to be the case. And we know Cn is some non-negative quantity. So when you multiply Cn with this, the inequality still remains the same. Okay, when the inequality is happening for all the n values, we can sum it up and still the inequality remains the same. That is summation n runs from 1 to infinity Cn I of x minus Sn less than or equal summation n runs from 1 to infinity Cn I of y minus Sn. Right? And this very well concludes that whenever x smaller than y, that implies alpha of x smaller than or equals alpha of y. Okay, this tells us that alpha is monotonically increasing. Okay, now let us talk about the convergence. Using the convergence, let us talk about something. We are okay. We have summation Cn converges by Cauchy criterion for convergence of series. We write for given epsilon positive, there exists an integer, actually a positive integer n, such that summation n runs from n plus 1 to infinity Cn is less than epsilon. So this is what the Cauchy criterion for the convergence of series tells us. And now let us consider alpha of x. This is what summation n runs from 1 to infinity Cn I of x minus S1. This summation we split into two terms. That is summation n runs from 1 to n Cn I of x minus Sn plus summation n runs from n plus 1 to infinity Cn I of x minus Sn. Okay, so this one we take it as alpha 1 of x plus this one alpha 2 of x. Okay, so alpha of x is split into sum of two terms. We know that if alpha of x is alpha 1 of x plus alpha 2 of x, then integral a to b f d alpha can be written as integral a to b f d alpha 1 plus integral a to b f d alpha 2. This is one of the properties of integrals. Using this property, we are going to evaluate this. So hence, let us mark this as equation 1. Now let us consider integral a to b f d alpha 1. Okay, so this is integral a to b f d of alpha 1 is what? Summation n runs from 1 to infinity Cn I of x minus Sn. So each of your, actually your alpha 1 is also a sum of finite number of terms. Only for finite number of terms we can split things out. That is why, sorry, actually here it is n. Only for finite number of terms we can split things out. Hence we are going to do so. Which means what? We are going to have summation n runs from 1 to n integral a to b f of d Cn I of x minus Sn. So this is what we are going to have. Okay. And again using one of the property, we can take Cn outside. Properties of an integral, using the properties of an integral, we can take Cn outside. So we would have integral a to b f d of x minus Sn. Using the previous theorem, this is nothing but simply the point of the function f evaluated at the point Sn. So this would give us n runs from 1 to infinity Cn f of Sn. So we have calculated the first, that is for alpha 1 of x, we have calculated the integral value. Now for the second case, that is consider integral a to b f d alpha 2. Okay, here let us take m to be the supremum of absolute of f of x and alpha of b minus alpha of a is smaller than epsilon. Let us consider this way. Okay, and what shall we do now? Okay, now let us evaluate integral absolute of integral a to b f d alpha 2. This is smaller than or equals integral a to b absolute of f d alpha 2. So this is by the property, right? And this quantity, by this assumption, this quantity is m times of integral a to b d alpha 2. Since m is a constant, we took it outside, and this is going to be what? M of, actually this is alpha 2 only. Okay, alpha 2 of b minus alpha 2 of a is smaller than epsilon. This is our assumption. This is going to be alpha 2 of b minus alpha 2 of a. By our assumption, what we are going to have is integral a to b f d alpha 2 is smaller than or equals m epsilon. Right? Now let us go back to our equation 1. Equation 1 tells us what? By equation 1, what we have is integral a to b f d alpha. This integral a to b f d alpha 1. So this quantity we have evaluated, that is summation n runs from 1 to n Cn f of Sn plus this quantity is integral a to b f d alpha 2. Okay, so from this integral a to b f d alpha, if you take the first term of the right hand side to the left hand side, you would get minus n runs from 1 to n Cn f of Sn is equal to integral a to b f d alpha 2. Okay, let me do the remaining part here itself. Okay, this is when you take the absolute value, it is absolute integral a to b f d alpha minus summation n runs from 1 to n Cn f of Sn is equal to absolute of integral a to b f d alpha 2, and if you mark this as equation 2, by equation 2 we get integral absolute of integral a to b f d alpha minus summation n runs from 1 to n Cn f of Sn smaller than or equals m epsilon. As n becomes large and large, as n approaches infinity, This gives us that absolute of integral a to b f d alpha minus summation n runs from 1 to infinity cn f of Sn is 0. This variable tells us that integral a to b f d alpha is summation n runs from 1 to infinity cn f of Sn, and this is what we intended to prove, hence the proof.